This video is on elliptical orbits. A satellite of mass m is in elliptical orbit around a celestial body, planet or star, of mass M. 2 points on m's orbit are shown, labeled 1 and 2. State one specific piece of information about M's location within the ellipse. And the answer to that would be the celestial body is at one of the focus points. And this is true for the sun in our solar system. As the planets go around, the sun is actually at one of the focus points. We've been asked now to draw position vectors R1 and R2 into the figure, so let's do that. There's position vector R1, and here's position vector R2. It starts at the star and goes to the planet and points at the planet. In the correct direction and to an appropriate length, draw vectors v1 and v2 into the figure. At point 1, the planet is going to be going slower. So if we were to draw a velocity vector there, we would draw it having a certain magnitude. And the velocity vector that we draw here for 2 should be larger. And those velocity vectors should be tangent to the elliptical path. To review, write equations for kinetic energy and absolute gravitational potential energy. Kinetic energy, we know and love to be 1/2 mv squared, and absolute gravitational potential energy is negative big G, big M, little m, divided by the distance between them. What we want to do now is match each of these terms here with one of these descriptors. And we can see from the equation that kinetic energy must always be positive. And so that means that the choices over here that have positive, those have to be the kinetic energies. It's just a question of which is which. At point 1, we're moving slower. So that must mean K1 is small and positive, which means K2 has to be large and positive. We can see here that gravitational potential energies are negative. And as R gets bigger, that magnitude is going to be smaller. And so what we're seeing here is that if R1 is a big value, then UG for point 1 is going to be a small negative value. So this one here, let me jump over, whoop, like that. And then U gravitational for point 2 is going to be a rather larger number, and it will also be negative. We're now going to write an equation that illustrates conservation of mechanical energy for the satellite, for point 1 and for point 2. For point 1, we have kinetic energy 1/2 m v1 squared plus negative big G, big M, little m divided by R1, not R1 squared, just R1. That's for point 1. For point 2, then its kinetic energy is going to be 1/2 m v2 squared, and its gravitational potential energy is going to be opposite big G, big M, little m divided by R2, like so. We can see that the common term that we have here is little m, and that's it. Why don't we simplify this as much as we can, and we'll just cancel out little m, and then we'll leave it at that. So this will simplify to 1/2 v1 squared minus G big M divided by R1, and that's going to equal 1/2 v2 squared minus G big M divided by R2. That's conservation of mechanical energy for this case. And mechanical energy is conserved because there's no friction in space. So let's assume that we know the values of r and the velocities. Let's solve the equation I've boxed in here at the top. Let's solve that for m. We're going to take this gm over r2, and we're going to put that on the other side of the equation first. gm over r2. It shows up positive there. I'm going to leave the other potential energy term on the left, like that. And now I'm going to move this kinetic energy at point 1, I'm going to move that over to the other side. So on the right side, we're going to have 1/2 v2 squared minus 1/2 v1 squared. And now let's go ahead and solve this for m. Let me factor out a gm here first. Gm on the left times the quantity 1 over r2 minus 1 over r1. And on this side, let's put the 2 in the denominator. All right. And in the numerator, let's put v2 squared minus v1 squared. To solve this for m, then I can put the g in the denominator under here. So let me just go ahead and do that. Put the g there. That goes away. And then I'm just going to take this whole term in parentheses, and I'm just going to put that in the denominator, like this. v2 squared minus v1 squared over, put the 2g there, and then let's take that term that has the r's in it. There we go. Now we've got fractions in the denominator, and your math teacher probably wouldn't be too happy with us about that, but to get rid of that would be more trouble than it's worth. We have solved this for the mass of the thing that is orbited. All right, nearly done. Thank you for hanging with me here. What condition must be true for angular momentum to be conserved? So this is a review question. No net torque on the system. For angular momentum to be conserved, no net torque. So into our figure, let's draw and label the gravitational force vectors. And the force of gravity is going to pull this way. Fg, I'll call it Fg1. And then we have Fg2 is going to pull this way, and it should be bigger. I'm trying to make that a little bit bigger. Fg at point 2, just like that. And does this show that there's no net torque on the system? And the answer is it does. If the line of action of a force, in this case gravity, acts on an object's center of mass, that force exerts zero torque on the object. So as this planet goes around the sun, there is no torque, no net torque. And for that reason, the angular momentum is conserved. So not only is mechanical energy conserved here, but angular momentum is also conserved. Assuming m to be the sun, label the points of aphelion and perihelion into the figure. If m were Earth, those points would be the apogee and the perigee. The nearest point is the one that starts with P. So that one's over here. So on this side right there, I'll put a little X there. That's going to be, if we have the sun, it's perihelion. If M is the Earth, like we have the moon going around, that would be the perigee. G for Earth, the prefix hel stands for the sun. And the point that's furthest away from the sun, that would be aphelion. And the point that's furthest away from Earth, if we're orbiting the Earth, is apogee. G stands for Earth. Like geology, Earth geology. One way I remember this is A is away, aphelion, apogee is away. That's the farthest away. And you might have heard that there's a tissue called the pericardium, and it surrounds the heart. It's like right outside the heart. So maybe that'll help you remember that perihelion and perigee is close to the orbited thing. Last question. For the terms in part X, conservation of angular momentum boils down to a real easy equation. Why is a similarly simple equation not applicable for any other points? For the apogee and perigee points, for example, R and V are perpendicular to each other. And so whenever you are doing the cross product, the magnitude of it requires us to use the sine of theta. Well, the sine of 90 is 1. So at those points, we have a really easy relationship between how far away and how fast. At other points, the sine theta is a more complicated decimal.